A better way for pilots to make sense of how density affects airplane performance is to use something called density altitude. Density altitude is a way of describing how the airplane will perform when put in context of an altitude. Scientists have developed a formula that allows them to assign a specific value for temperature and pressure to different altitudes. We call these designated values the standard atmospheric conditions for those altitudes. The standard conditions for 0 feet elevation, or sea level, consist of a temperature of 15 degrees Celsius and a pressure of 29.92 inches of mercury. Let's take an example of a Cessna departing from an airport at sea level. If the temperature is 15 degrees Celsius and the pressure is 29.92 inches of mercury, the plane would perform as if it's flying at a density altitude of 0 feet. If that same airplane were to depart from the same airport on a different day with different weather conditions, we would use the non-standard temperature and pressure to determine what density altitude those conditions would represent. For instance, if the temperature was 32 degrees Celsius and the pressure was 30 inches of mercury, this would be the equivalent of a density altitude of approximately 2,100 feet. The pilot would then know to expect the same performance he or she would get at 2,100 feet instead of sea level. This would result in the plane using up more runway to take off and having a slower climb up to the desired cruising altitude. Performance charts from aircraft manufacturers are published so pilots can take the changing weather conditions into account when they're calculating aircraft performance. These charts provide a simple graphical way of determining density altitude without the pilot needing to perform complex math problems to get the same results. Let's say we will be flying at 5,000 feet to our destination and want to find out what our density altitude will be. For simplicity, we'll use a density altitude chart. The first step involved is to calculate our pressure altitude, which corrects for our non-standard pressure. Let's say today's pressure is 30.10 inches of mercury. Looking at the right side of the chart, we look into the left column for the altimeter setting of 30.10 and find that the pressure altitude conversion factor in the right column is negative 165. That means that our pressure altitude is 165 feet lower than what's indicated. 5,000 feet minus 165 feet equals a pressure altitude of 4,835 feet. If we were to enter 29.902 in our altimeter's Coleman window, it would read 4,835 feet. Now that we have our pressure altitude, we need to correct for non-standard temperature, giving us our density altitude. Let's say that the current outside temperature read of the air is about 4 degrees Celsius. Starting at the bottom of the chart, find the 4-degree mark. Next, follow the vertical lines upward until we intersect the diagonal pressure altitude of 4,835 feet. Then, follow the horizontal lines to the left edge and read the altitude. That would result in the approximate altitude of 4,600 feet. Today's relatively high pressure and low temperature resulted in a lower density altitude, which means the plane will perform as if it were flying at a lower altitude, giving it an increase in performance. So now that we are able to determine pressure and density altitudes, we can take a closer look at how this affects the airplane. To see some examples of how the performance will change in different scenarios, let's look at Chapter 5 of the Cessna 172S Pilot's Information Manual. The Pilot's Information Manual contains performance charts for the different phases of flight, including takeoff, climb, cruise, and landing. Remember that each aircraft manufacturer creates their performance charts differently, so be sure to study them carefully before you actually use them. Let's start off by looking at the short field takeoff distances for 2,400 pounds. The distances shown are for ground roll and for clearing a 50-foot obstacle. The aircraft's ground roll is how far down the runway the airplane must travel to accelerate from a standing start to a rotation speed of 51 knots. The column labeled total feet to clear a 50-foot obstacle gives the distance the plane will travel, accelerating from a standing start to takeoff, and then climb to an altitude of 50 feet. On the chart, the far left column shows the pressure altitude, and the top row shows temperature. In essence, the chart will calculate the effects of density altitude for you. Let's say, for example, our pressure altitude is sea level and the temperature is 0 degrees Celsius. If we look at the intersection of these two values, we find that the takeoff distance is 745 feet. As the temperature increases, notice how the takeoff distance increases. At 20 degrees Celsius, the takeoff distance increases to 860 feet. And at 40 degrees Celsius, the takeoff distance increases to 995 feet. This results in a total difference of 250 feet increase just from the temperature rising. Now let's look at altitude changes. A sea level pressure altitude and a 0 degree temperature results in a takeoff distance of 745 feet. At a pressure altitude of 5,000, like you would find at ERAU's Prescott, Arizona campus, the takeoff roll is 1,170 feet. That results in a difference of 425 feet. Now, imagine a hot summer day with a pressure altitude of 5,000 feet and a temperature of 30 degrees Celsius. The takeoff distance in that situation would be increased to 1,465 feet. That's nearly double the distance compared to what it would have been at sea level and 0 degrees. The aircraft's airspeed indicator reads off what we call indicated airspeed. This airspeed only takes the pressure of the air into account instead of all of the density factors. Because of that, our true airspeed may be different from the indicated, depending on the temperature and humidity. On days where the air density is low, the aircraft will have to travel faster to get the same indicated airspeed. This results in increased takeoff distances. The wind direction and speed play a big role in takeoff distances as well. For the airplane to take off, it needs to reach a speed of 51 knots. If there's an 18-knot headwind, it's almost like saying the airplane has an 18-knot head start and only needs to accelerate 32 more knots to get 51 knots of wind flowing over the wings. This would reduce the runway required from 745 feet down to only 596 feet. A tailwind would do just the opposite. If we were to have a mere 4-knot tailwind, the airplane would first have to travel at 4 knots just to counteract the wind. It would then have to continue accelerating an additional 51 knots to be able to take off. That means that over the ground, the plane would have to accelerate up to 55 knots to take off. And while a 4-knot increase doesn't sound like much, that little bit of wind would increase the takeoff roll to 894 feet, an increase of 150 feet. Another factor to consider in the performance of an airplane is its weight. Heavier airplanes require more power and thrust. Simply put, the heavier the airplane is, the lower its performance would be. For takeoff distances, a heavier airplane would need more distance in their roll. This is because it takes more power to get the airplane rolling and accelerate to rotation speed. If we stick to our sea level pressure altitude and 0 degree temperature, the 2,400-pound Cessna would require a takeoff distance of 745 feet. If the weight was increased to 2,550 pounds, the takeoff distance would increase to 860 feet. If we instead decreased our weight to 2,200 pounds, the distance would decrease to only 610 feet. For those 350 pounds, we'd get a difference in takeoff distance of 250 feet. After our takeoff is accomplished, the next stage of flight is the climb. Our next chart not only shows the rate of climb that the airplane will get, but also includes the time, fuel, and distance the airplane will use to get to our cruising altitude. Looking at this chart, we can understand the trends as an airplane climbs higher and higher. Notice in particular how the climb rates decrease with altitude. As the airplane climbs, the density decreases, and this decreases performance. So, at sea level, the best rate of climb speed is 74 knots, and the vertical climb rate is 730 feet per minute. At 8,000 feet, the best rate speed lowers to 72, and the climb rate drops to 410 feet per minute. Temperature will also affect these numbers. The note at the bottom of the page states that all time, fuel, and distance numbers increase by 10% for every 10 degrees above the standard temperature. Weight changes will also affect these performance values. While Cessna does not publish the performance values at lighter weights, if the airplane did weigh less than 2,550 pounds, the airplane should climb at a greater rate than the published numbers. However, since Cessna does not publish the information, we plan for the most conservative scenario at the 2,550-pound weight. This next chart shows the cruise performance of the airplane, displaying the airspeed, fuel burn rate, and percent of maximum continuous power in relation to different temperatures and altitudes. At 4,000 feet with an engine RPM setting of 2,500 RPM and at standard temperature, in this case 7 degrees Celsius, the airplane will be at 69% power at 115 knots and use up 9.5 gallons per hour. If the temperature were to rise to 27 degrees, the power output would drop to 64%. The speed would reduce to 114 knots, and fuel burn would decrease to 8.9 gallons per hour. This happens without ever touching the throttle. The reduced air density gives both a drop in performance and a drop in fuel burn because the engine has less air molecules available to use. If the temperature were to drop to negative 13 degrees Celsius, the increased air density would boost the engine power to 74%. Increase the speed to 115 knots, and consequently also increase the fuel burn to 10.1 gallons per hour. The different power settings available at each altitude give the pilot more flexibility in flight planning and choosing the one that best fits the flight plan. If we also look at the range and endurance charts, we can see how changing the RPM of the engine can greatly affect both how far we can travel and how long we can stay in the air. By simply going slower, we can actually travel over 100 miles further on one tank of gas. If your destination is about as far away as your current maximum range, it may be wise to slow down to a lower power setting. You'd be able to make it all the way there without needing to stop for fuel. Just like the takeoff, landing distances will also vary with the weight of the airplane, the outside air temperature, and the airport field elevation. Cessna only publishes landing data for an airplane at the maximum gross weight of 2,550 pounds. But lighter airplanes will be able to fly a slower approach speed for landing and will have less momentum and less energy to dissipate once on the runway, resulting in a shorter rollout. Just like before, make sure you use the published data to calculate your runway distance required before flight. Here is how temperature and pressure affect the landing distance in the Cessna 172. At sea level and at 0 degrees Celsius, the Cessna will need 545 feet to land. As the temperature increases, the distances increase all the way to 625 feet at the 40-degree mark. Just like the takeoff performance charts, this chart shows the distance required not only for ground roll, but also for the distance to clear a 50-foot obstacle and then land and come to a complete stop on the runway. The chart also shows the landing distances increase as altitude increases. Here, the distance of 545 feet at sea level increases to 655 feet when at 5,000 feet. Wind will also affect the landing roll. A headwind of 9 knots will reduce the landing distance by 10%, and a tailwind of just 2 knots will increase the landing distance by 10%. So, landing at sea level with a temperature of 0 and a headwind of 18 knots will reduce the landing distance from 545 feet down to 436 feet. The examples we just used were based on the performance of a Cessna 172S, but the general concepts apply to all airplanes. Regardless of what you fly, weather conditions have a significant impact on aircraft performance. Doing your performance calculations prior to each flight is a critical part of your pre-flight planning. By understanding how the temperature, pressure, and altitude can affect your aircraft's performance, you can ensure a safe and enjoyable flight every time you take to the air.